There's a planet 77 million kilometers from here that scientists have been trying to explain for decades. And they can't. Not because they lack data, but because the data they have doesn't fit any model we've ever built. It has the largest iron core in the solar system relative to its size. It has ice on the planet closest to the sun. And it has a geological history suggesting that something enormous, something catastrophic, completely transformed it billions of years ago. Today, we're going to tear it all apart. What you think you know about Mercury is wrong. And by the end of this video, I'm going to tell you something almost no documentary ever mentions. Something the Messenger mission found in its final months, just before it crashed into the surface at 14,000 kilometers per hour. Stay with me. Mercury, the first planet in our solar system, the closest to the sun, and probably the most misunderstood of all. Most people dismiss it. It's small, it's hostile, no moons, no rings, no real atmosphere. But here's the problem. The more we study it, the more questions appear. It has the most disproportionate iron core in the entire solar system. It has ice at its poles, despite surface temperatures hitting 430 degrees Celsius. And it has a geological history, suggesting that what we see today isn't what it always was. Something happened to it, something massive, and we still don't know exactly what. Today we're going through it all. What science has found in the last 20 years, what the Messenger mission discovered up close, and what Bepi Colombo might reveal before 2030. By the end of this video, I'm going to tell you something almost no documentary mentions. Something that could change how we understand the formation of our entire solar system. Let's start with the basics, because even the basics with Mercury are surprising. Mercury is the smallest planet in the solar system. Diameter, 4,879 kilometers. To put that in perspective, it's smaller than Ganymede, Jupiter's moon, smaller than Titan, Saturn's moon. There are moons of other planets that outsize it, and yet, it's a planet. It takes 88 Earth days to orbit the sun. Fast. Makes sense. The sun's gravity pulls it along furiously. But here's the first thing almost no one mentions. It takes 59 Earth days to rotate on its own axis. That means its day is longer than its year. Wait, that's not even the strange part. The combination of its orbital speed and its rotation creates what physicists call a 3-to-2 resonance. For every 2 complete orbits around the sun, Mercury rotates exactly 3 times on its axis. And what does that mean for someone standing on the surface? The sun rises, stops, moves backward, stops again, then continues forward. The sun moves in reverse across Mercury's sky. Let me say that again. The sun goes backwards on Mercury. This was so confusing that astronomers assumed for decades that Mercury always showed the same face to the sun, like the moon does with Earth. They were completely wrong. It wasn't until 1965, with radar observations from Earth, that astronomer Gordon Pettengill proved Mercury was rotating. In that strange resonance nobody had predicted. 20 years of wrong textbooks. 20 years. And that's just the beginning. Because when we start talking about Mercury's interior, things get genuinely weird. Now we get to what scientists call the Mercury problem, the core. In a normal planet, the internal structure follows a pattern: outer crust, mantle, and at the center, an iron-nickel core. On Earth, that core represents about 17% of the planet's total volume. On Mercury, the core represents between 55 and 60% of total volume. Think of an orange. Normally, the peel and pulp are most of it. On Mercury, almost everything is seed. Why? We don't know for certain. The leading theory is dramatic. About 4 billion years ago, Mercury was a larger planet, a thicker crust, a more developed mantle, something closer, in some ways, to Earth. Then something hit it, an object the size of a small planet, a brutal, catastrophic collision. The energy was enough to literally strip Mercury's outer mantle away. The outer layers were blasted into space. What remained was the core, with very little on top. It's exactly what's believed to have happened to Earth when the moon formed, a giant impact that ejected material. Except in Mercury's case, that material didn't form a moon. It dispersed. It was lost. But here's the detail nobody talks about. If Mercury lost its mantle in that impact, where did that material go? Could some of that iron and silicate have ended up in Venus? In Earth? Computer simulation models suggest yes. That part of the material composing Earth's mantle could have originated in that ancient, larger Mercury that no longer exists. We may carry Mercury's fingerprint inside us. Then there's the magnetic field. A planet Mercury's size, with that composition, as cold as it is today, should not have a magnetic field. Models predict its core should be solidified, no movement, no dynamo, and yet Mercury has a magnetic field, small, weak, tilted relative to its rotation axis. But it's there. How? We still don't fully know. What we do know is that this magnetic field is so asymmetric that it's significantly stronger in the northern hemisphere than the southern. And that asymmetry, no model predicted was possible in a planet this small. Drop that in the comments if you knew this, because it still stops me cold every time. Mercury has ice. Yes, ice, frozen water, on the planet closest to the sun. Before your brain collapses, let me explain. Mercury has an axial tilt of just 0.03 degrees, essentially zero. That means its poles always point perpendicular to the sun. No seasons. No variation in illumination angle throughout the year. The floors of craters at the poles have never, not once, been hit by direct sunlight. Never. In those permanently shadowed floors, temperatures drop to minus 180 degrees Celsius, 180 below zero, on the same planet where the sunlit surface hits 430 degrees positive. A difference of over 600 degrees between different points on the same planet. And in those permanent shadow zones, there's frozen water. This was first suspected in 1991, when radar telescopes from Earth detected unusually bright reflections at Mercury's poles, the kind of reflection ice produces. Definitive confirmation came in 2012, when the Messenger probe captured the first direct images of those craters. What it found exceeded every estimate. Not thin ice films, not residual traces, up to 100 meters of ice depth in some North Pole craters. The total amount of frozen water at Mercury's poles is estimated in the hundreds of billions of tons. But there's something else in those polar craters. Messenger detected not just ice, it detected organic matter, complex carbon compounds mixed with the ice. Not life, let's be clear, but the chemical building blocks from which life could emerge under different conditions. Organic matter, on Mercury, 57 million kilometers from the sun. Starting to see why this planet breaks every rule? And the thing almost no documentary mentions is still coming. Hold on. There's a region on Mercury called the Calorus Basin, Calorus, from the Latin heat, and the name fits. It's the hottest region on the planet when facing the sun, and it's the largest scar in Mercury's history. The Caloris Basin is 1,550 kilometers in diameter. Picture a crater covering all of Western Europe, from Lisbon to Warsaw. It formed roughly 3.9 billion years ago during what astronomers call the Late Heavy Bombardment, a period when a rain of asteroids and comets hammered all the inner planets. The object that created Caloris was enormous. Estimates suggest an asteroid between 100 and 150 kilometers across. The impact released energy equivalent to trillions of nuclear bombs. But the truly astonishing thing about Caloris isn't the crater itself. It's what's on the exact opposite side of the planet. When that asteroid hit Mercury, seismic waves traveled through the entire planet, through the core, through the mantle. And when they reached the point directly opposite the impact, they all arrived at once. The result was a region of completely shattered terrain, chaotic hills, irregular cliffs, a landscape that looks like someone shook it from below. Geologists call it the chaotic terrain, or informally, the weird terrain. It is literally the point where the shock waves of Mercury's greatest impact converged from the other side of the world, like firing a bullet through one end of an apple and having the other end explode. And inside Caloris itself, there are mountains, concentric mountain rings reaching up to 3 kilometers high, a full mountain system inside a crater large enough to fit Europe. The heat from the collision reactivated internal volcanism. Lava flowed back into the crater and reshaped it. Caloris isn't just a wound, it's a place where the planet rebuilt itself after the blow. The models didn't predict that either. In October 2018, the European Space Agency and Japan's Space Agency launched a joint mission that could answer many of these questions. Its name is Bepi Colombo. It will enter Mercury's orbit in 2025, and its instruments are significantly more precise than Messenger's, capable of imaging surface details down to 10 meters per pixel. 3 major questions Bepi Colombo has a real chance of answering. What keeps Mercury's core active? Why didn't it solidify? What exactly are the polar deposits made of? What types of organic molecules are there? Is the magnetic field asymmetry stable, or is it changing? Before 2030, we should have answers. But now, the thing I promised you at the beginning, the thing almost no documentary mentions. In Messenger's final months of operation, before it ran out of fuel and crashed into Mercury's surface, its instruments detected something in the surface chemical composition that didn't fit. Certain regions of the northern hemisphere showed significantly higher concentrations of sulfur and carbon than expected. Not in the polar craters, on the open surface. In 2016, mission geologists published a paper suggesting these concentrations could indicate the presence of graphite, crystallized carbon, a layer of graphite buried just beneath Mercury's crust. Where would that graphite have come from? The most accepted hypothesis is extraordinary. In Mercury's earliest days, when the planet was still completely molten, the magma ocean floated carbon at its surface, like residue floating in broth. And when that magma ocean cooled, that carbon was buried just beneath the crust. Mercury may have a graphite layer beneath its feet, a dark crystalline shell lining the interior of the smallest planet in our solar system. And that carbon is the same base element as life on Earth. I don't know if that has direct implications for Mercury's habitability. Probably not, but it seems impossible not to ask. If the carbon is there, if organic molecules are in the poles, if the planet may have had more temperate conditions billions of years ago, what else don't we know? Mercury has been there since the beginning, 4.5 billion years. It survived bombardments, giant impacts, the loss of its mantle, the sun growing hotter, and we still don't fully understand it. The closest planet to the sun, the one that should be easiest to study, the one we visited less than Mars, Jupiter, Saturn, and it turns out to hold more unanswered questions than almost any of them. That says something about what we assume we know. If this video made you think, subscribe, hit the bell, and tell me in the comments which facts surprised you most. Mine is always the graphite, until the next mission. Venus and Earth are twins, same size, same mass, same composition, formed at the same time from the same cloud of gas and dust, just a few 100 million kilometers apart. Today, Earth has oceans, forests, and 8 billion people. Venus has a surface temperature of 465 degrees Celsius, an atmospheric pressure 92 times greater than Earth's, enough to crush a nuclear submarine, and clouds made entirely of sulfuric acid. We share the same origin. We ended up in completely different universes. And here's the part that should make you very uncomfortable. We don't fully understand how Venus got this bad, which means we don't fully understand whether Earth could follow the same path. By the end of this video, I'll tell you about a discovery made in 2020 that split the scientific community in half and still hasn't been resolved. A discovery that forced us to ask whether we have been completely wrong about what Venus is. Let's go. Venus and Earth are twins, same size, same mass, same composition, same origin story, formed from the same cloud of gas and dust in the same neighborhood of the early solar system, roughly 4.5 billion years ago. On paper, they should be nearly identical. They are not. Earth has liquid oceans, a breathable atmosphere, a temperature range where water stays liquid, 8 billion living things clinging to its surface. Venus has a surface temperature of 465 degrees Celsius, day and night, at the poles and at the equator, always. Its atmospheric pressure is 92 times greater than Earth's. If you stood on the surface of Venus without a suit, you wouldn't burn to death first. You'd be crushed, like a submarine diving 20 times too deep. Its clouds, the thick, brilliant white clouds that make Venus the brightest object in our night sky after the moon, are made of sulfuric acid droplets. They don't produce rain. They produce acid that evaporates before it hits the surface, and Venus rotates backwards. Compared to every other planet in the solar system, its spin is reversed, and it rotates so slowly that a single Venusian day is longer than a Venusian year. This is Earth's twin, and we still don't completely understand how it got this way. That's what we're here for today. Because the answer, or the attempt at an answer, is one of the most important stories in planetary science. And it has implications that go far beyond Venus. Stay with me, because this gets genuinely unsettling. Nobody had ever seen the surface of Venus until 1975. Because you can't, not from space, not with optical telescopes. The cloud layers are permanent and completely opaque. Venus hides its surface behind an unbroken ceiling of acid cloud that extends from about 45 to 70 kilometers altitude. The only way to know what's underneath is to go there. The Soviet Union tried, repeatedly. Between 1970 and 1985, they sent a series of landers called Venera to the surface of Venus. This was one of the most extraordinary engineering achievements of the space race, and one of the least talked about. The problem was simple and almost insurmountable. The surface of Venus destroys everything. The first landers were crushed by the pressure before they could transmit a single image. The engineers went back, redesigned, added more shielding, more insulation, made the spacecraft look like pressure vessels, because that's essentially what they were. Venera 9 and Venera 10, landing in 1975, finally survived long enough to send back photographs. The first photographs ever taken from the surface of another planet in our solar system beyond the Moon. Not Mars, Venus. The Soviets got there first, and what they showed was not what anyone expected, not a smooth, molten, featureless hell. Instead, rocks, jagged, angular rocks, geological features, terrain that looked, in some ways, disturbingly geological, almost familiar, except bathed in an orange glow from the thick atmosphere filtering the sunlight above. The landers lasted between 23 minutes and 2 hours before the heat destroyed their electronics. Today, the best maps of Venus's surface come from radar. The Magellan spacecraft, orbiting in the 1990s, used radar to pierce the clouds and map 98% of the surface at 100-meter resolution. What it found was a world dominated by volcanism, vast volcanic plains covering most of the surface, thousands of volcanoes, more volcanoes than any other planet in the solar system, a handful of highland regions that may be ancient continental remnants, and almost no impact craters, which tells us the surface is geologically young. Something resurfaced the entire planet within the last 300 to 500 million years. Something enormous happened, and we think we know what it was. Here's the thing about Venus that most people don't know. It may not have always been hell. In 2016, a team of scientists at NASA's Goddard Institute for Space Studies ran climate simulations of early Venus. What they found was striking. For potentially 2 to 3 billion years, a window that includes the period when life first appeared on Earth, Venus may have had a temperate climate, liquid water, oceans, a habitable surface. Let me say that again. Venus may have been habitable for longer than Earth has existed as a planet. The simulation depended on several assumptions. A slower initial rotation, which Venus may have had before tidal interactions with the Sun, gradually changed its spin, a shallow ocean covering much of the surface, and the younger, dimmer Sun providing less energy than it does today. Under those conditions, the model showed stable temperatures, a water cycle, a climate that, while different from Earth's, was within the range where liquid water could persist. Is this confirmed? No. It's a model, and models are only as good as their inputs. But here's what makes it plausible. We know that Venus has water, locked into its atmosphere as trace amounts of water vapor, and recorded in the chemistry of its rocks as evidence of past water activity. The ratio of deuterium to ordinary hydrogen in Venus's atmosphere is 150 times higher than on Earth. That ratio is a fingerprint. It tells us that Venus once had vastly more water than it does today. Water that has since been lost. Something took it. And here's where the story gets tragic. Because it wasn't a catastrophic impact that destroyed Venus. It wasn't a sudden event. It was physics. Slow, inevitable, unstoppable physics. And it has a name, the runaway greenhouse effect. The runaway greenhouse effect is not a metaphor. It's a specific, well-defined physical process. And it's the most terrifying thing I know of in planetary science. Here's how it works. Venus starts with liquid water oceans. Sunlight hits the surface. Some of it is absorbed, some reflected. The planet warms. As it warms, water evaporates. Water vapor enters the atmosphere. And water vapor is a greenhouse gas. It traps heat. So the atmosphere warms more, which evaporates more water, which traps more heat. This feedback loop, once it starts, has no natural break. On Earth, the carbon silicate cycle acts as a thermostat. When temperatures rise, silicate rocks weather faster, absorbing CO2 from the atmosphere, cooling the planet. A self-correcting system, imperfect, slow, but real. Venus lost that thermostat. As temperatures rose and oceans began evaporating, the weathering cycle couldn't keep up. CO2, released by volcanoes, no longer absorbed by liquid water and rock, began accumulating in the atmosphere. More greenhouse gas, more heat, more evaporation. The feedback loop ran away, completely. The oceans boiled. Not quickly. This took tens or hundreds of millions of years. But they boiled. The water vapor rose into the upper atmosphere, where ultraviolet radiation from the sun broke the water molecules apart. The hydrogen escaped to space. The oxygen combined with surface rocks or was swept away. The ocean simply ceased to exist. What remained was a thick, dense, CO2-dominated atmosphere. 96.5% carbon dioxide, 3.5% nitrogen, almost nothing else. That atmosphere creates the greenhouse effect we measure today, the 465-degree surface, the pressure that would crush a submarine. Venus didn't have a sudden catastrophe. It had a slow, self-amplifying disaster. And here's why this should concern you. The fundamental mechanism, rising temperatures increasing water vapor, which increases temperature, is the same feedback loop that climate scientists monitor on Earth. We have not triggered a runaway greenhouse on Earth. Our situation is categorically different. Earth is further from the sun, has more efficient cooling mechanisms, and has the carbon silicate cycle functioning well. But Venus tells us the feedback loop is real. It's not theoretical. It happened. That's not a reason for panic. It's a reason to understand it. And it's why studying Venus, understanding exactly how and when this tipping point was crossed, is arguably the most practically important thing we can do in planetary science right now. For decades, scientists suspected Venus might still be volcanically active. The surface is young, too young for a geologically dead planet. The atmosphere is constantly being resupplied with sulfur dioxide, a volcanic gas, in amounts that can't be explained by the existing atmospheric chemistry alone. But suspicion isn't evidence. In March 2023, a study published in Science provided the evidence. Researchers re-examined archival radar images from the Magellan spacecraft, images taken over 30 years ago, sitting in NASA's data archives. They compared images of the same volcanic region taken 8 months apart, in 1990 and 1991. In that 8-month window, a volcanic vent had changed shape, expanded, grown. On Earth, that kind of rapid morphological change in a volcanic vent has one explanation: activity, eruption, lava, heat. Venus is volcanically active, right now, today, as we speak. This isn't a minor update. It means Venus has an active geological cycle, active volcanism, heat coming from the interior, a planet that isn't simply a dead relic, but a living, geologically functioning world hidden under those clouds. And it changes the picture of the atmosphere, because active volcanoes release not just sulfur dioxide, they release water vapor, carbon monoxide, hydrogen sulfide, complex chemistry that interacts with the sulfuric acid cloud layers in ways we don't fully understand. It means the Venusian atmosphere is more dynamic, more chemically complex, and potentially more interesting than we thought. It also means that whatever killed Venus, the runaway greenhouse event, didn't kill its interior. The engine is still running, and that engine creates chemistry. And chemistry, in the right conditions, can create something else entirely. Which brings us to the discovery that split the scientific world. In September 2020, a team of astronomers led by Jane Greaves at Cardiff University announced something that made headlines around the world. They had detected phosphine in the atmosphere of Venus. Phosphine, pH3, a molecule of phosphorus bonded to 3 hydrogen atoms. On Earth, phosphine is produced in 2 ways: industrial chemical processes and biological processes, specifically by anaerobic microorganisms, microbes that live without oxygen. In the atmosphere of Venus, there is no obvious non-biological chemistry that should produce phosphine in the concentrations detected. The sulfuric acid clouds destroy it. The UV radiation breaks it down. Whatever is producing it must be producing it continuously, in significant quantities. The paper suggested a remarkable possibility: microbial life, floating in the cloud layers of Venus. At altitudes between 48 and 60 kilometers, where temperatures and pressures are remarkably close to those at Earth's surface. Around 30 degrees Celsius, 1 atmosphere of pressure. The most habitable zone on Venus isn't the surface, it's 50 kilometers above it. This sent the scientific community into immediate, productive chaos. Some researchers tried to reproduce the detection and couldn't find phosphine at the concentrations originally reported. The original data was reanalyzed. The signal, some argued, was weaker than initially claimed, or possibly an artifact of the instrument. Others proposed non-biological explanations: unusual volcanic chemistry, photochemical reactions involving sulfur compounds, processes we hadn't considered. The debate has not been resolved. What everyone agrees on is this: we cannot currently explain the full atmospheric chemistry of Venus. There are things happening in those clouds that our models don't account for. Whether those things involve biology or exotic chemistry, we don't know. And we won't know until we go back, really go back, with instruments designed specifically to look for biosignatures in the cloud layer, where the conditions are actually genuinely survivable. Tell me in the comments, do you think there's life in the clouds of Venus? Because this question deserves to be asked out loud. Before 2032, 2 missions will change everything we know about Venus. Da Vinci, deep atmosphere, Venus investigation of noble gases, chemistry and imaging, a NASA mission that will drop an instrumented probe through Venus's atmosphere, measuring its chemistry layer by layer, and then image the surface of a Venusian highland region called Alpha Regio in detail never seen before. Da Vinci will tell us definitively whether Venus once had oceans. The noble gas ratios and isotopic signatures in the deep atmosphere are preserved records of the planet's history, like reading tree rings, but for an entire planet. And Veritas, Venus emissivity, radio science, INSAR, topography and spectroscopy, an orbital mapping mission that will produce topographic and compositional maps of Venus at a resolution 10 times better than Magellan. With Veritas, we'll be able to see individual geological features, identify which volcanoes are currently active, map the distribution of minerals that would tell us where water once existed, and perhaps find the remnants of ancient shorelines, if they exist. These 2 missions together represent the most comprehensive Venus exploration since the Soviet Venera program ended in 1985. 40 years of waiting, ending before 2032. And here's why this matters beyond pure science. Venus is not just a fascinating dead world, it's a data point. The most important data point we have for understanding the limits of planetary habitability. We know of 3 rocky planets in the inner solar system with roughly similar compositions and sizes: Venus, Earth, and Mars. Mars lost its magnetic field and its atmosphere and went cold. Venus triggered a runaway greenhouse and went hot. Earth sits in between, and we still don't know precisely how wide that window is. Venus tells us the hot edge of the window. Understanding exactly when and why Venus crossed that edge, what the tipping point was, whether it was inevitable, or whether a slightly different set of initial conditions could have saved it, is directly relevant to understanding the long-term stability of Earth's climate. Not in a scaremongering way. Earth is not Venus. The differences are real and significant. But Venus tells us that planets can go wrong, that the conditions for life are not automatically self-sustaining, that a world can transform from habitable to hellish through processes that are, in principle, measurable and understandable, which means they are, in principle, preventable. Venus is not a warning about tomorrow. It's a lesson about physics, about what happens when feedbacks run away, about the conditions that make a world livable, and what can take them away. If you want to understand Earth's future, start by understanding Earth's twin. Subscribe, hit the bell, and let me know in the comments, which planet do you want us to cover next? Because we're just getting started. Until the next mission. 4 billion years ago, Mars had oceans. Real oceans, deep ones, covering almost a third of the planet's surface, with waves, with shorelines, with a sky that may have been blue. And then something happened, something so catastrophic that in the space of a few 100 million years, which is nothing geologically speaking, Mars went from being a world that looked disturbingly like Earth to the frozen, irradiated desert we see today. We know this happened. The evidence is written into the rocks, the valleys, the ancient shorelines still visible from orbit. What we don't fully understand is why. And what we've found beneath the surface in the last 5 years is making scientists very uncomfortable. By the end of this video, I'll tell you about a specific discovery from the Perseverance rover that almost nobody in mainstream media has covered properly. Something that changes the questions we're asking about Mars entirely. Let's go. Mars, the red and arid planet that we know today, had oceans. Real oceans. Deep ones. Covering almost a third of the planet's surface. With waves. With shorelines. With a sky that may have been blue. And then the unthinkable happened. Something so catastrophic that in the space of a few 100 million years, which is nothing in geological terms, Mars went from a world that looked disturbingly like Earth to the frozen, irradiated desert we see today. We know this happened. The evidence is carved into the rocks, written in the ancient riverbeds still visible from orbit, preserved in the chemistry of the soil. What we don't fully understand is exactly why. And what we've found beneath the surface in the last 5 years is making scientists deeply uncomfortable. Today, we're going through everything. The ancient Mars nobody talks about. The catastrophe that killed it. The geology that still breaks records. The water that's still there, just not where you'd expect. And the search for life that has produced one result the mainstream media has almost entirely ignored. By the end of this video, I'll tell you about a specific discovery from the Perseverance rover that changes the question we're asking about Mars entirely. This is not the Mars you learned about in school. Let's talk about what Mars actually was. Because the evidence isn't thin, it isn't speculative. The ancient surface of Mars is covered in features that can only have one explanation: liquid water, flowing, pooling, eroding, for millions, possibly billions, of years. There are valley networks, enormous ones, ancient river systems stretching thousands of kilometers across the southern highlands. These aren't wind formations. These aren't lava channels. The branching patterns, the erosion signatures, they are rivers. Full stop. There are deltas, places where those rivers emptied into standing bodies of water and dropped their sediment load, exactly like river deltas on Earth today. The Jezero crater, where the Perseverance rover is operating right now, is one of them. We landed a rover inside an ancient river delta on purpose. There are ancient shorelines, visible from orbit, running along the boundary of the northern lowlands at a consistent elevation for thousands of kilometers. The kind of feature that only makes sense if there was a sea level, a literal sea level, on Mars. And there's the chemistry. Everywhere we've drilled or scraped the Martian surface, we find minerals that only form in the presence of liquid water: phyllosilicates, sulfates, carbonates, the entire mineralogical fingerprint of a wet world. Mars wasn't wet for a brief moment. Some regions show evidence of water activity spanning billions of years. Now here's where it gets interesting. This ancient Mars, with its oceans and rivers and thick atmosphere, existed at roughly the same time that life first appeared on Earth. The same time window. Earth got life. Mars got what? That's the question scientists have been asking for 50 years. And in the last 5, the answers have started arriving. But first, we need to understand what killed it. Because what happened to Mars is arguably the most dramatic single event in the history of our solar system. About 4.2 billion years ago, something in Mars's core stopped. The planet's magnetic field, which had been shielding the surface from the sun's radiation and solar wind, simply collapsed. We know this because of the rocks. Ancient Martian rocks are magnetized. They recorded the direction of the magnetic field when they solidified, like a geological compass. And those records show a strong, active field early in Mars's history. Then the magnetization disappears, abruptly. In younger rocks, nothing. The field died. And when it did, the consequences were catastrophic and irreversible. Without a magnetic field, Mars had no protection from the solar wind, the constant stream of charged particles blasting out from the sun. That solar wind began stripping away the Martian atmosphere, molecule by molecule. It didn't happen overnight. It took hundreds of millions of years, but the trajectory was one way. As the atmosphere thinned, atmospheric pressure dropped. And as pressure dropped, liquid water could no longer exist on the surface. The boiling point fell below the freezing point. Water either evaporated into space or froze into the ground. The oceans didn't drain into cracks. They literally evaporated into a dying sky and were stripped away by the sun. The NASA MAVEN mission, which has been orbiting Mars since 2014, has measured this process directly. Right now, today, Mars is losing roughly 100 grams of atmosphere per second to the solar wind. 100 grams per second, every second, for billions of years. The question scientists have argued about for decades is, why did the core stop generating the magnetic field? Mars is smaller than Earth. It cooled faster. When a planetary core cools completely, the convection that drives the magnetic dynamo stops. But the timing is the problem. Mars's core cooled unusually fast, faster than the models predicted for a planet its size. And some researchers now believe the answer involves a series of massive asteroid impacts early in Mars's history that disrupted the core's heat distribution. One catastrophe triggering another. A chain of events that turned a living world into a desert. And it raises a question that nobody can quite shake. If Earth's core ever cools, are we next? Before Mars died completely, it did something extraordinary. It built the largest volcano in the solar system, Olympus Mons, with an height of 22 kilometers above the Martian surface, roughly 2.5 times the height of Mount Everest. Its base is so wide, 600 kilometers across, that if you stood at the center, you couldn't see the edges. They'd be beyond the horizon. You would have no idea you were standing on a volcano at all. And here's the thing about Olympus Mons that most of us miss. It got so big because Mars doesn't have tectonic plates. On Earth, the crust moves. A volcanic hotspot under the crust, like the one under Hawaii, punches through periodically, but the plate moves, so you get a chain of islands. The hotspot doesn't stay under the same point long enough to build anything truly enormous. Mars's crust doesn't move. The hotspot stayed in exactly the same place for billions of years. Eruption after eruption after eruption, all in the same spot, all piling on top of each other. The result is the massive volcano Olympus Mons. And Olympus Mons isn't alone. The Tharsis Bulge, the volcanic plateau it sits on, is 5,000 kilometers across and 10 kilometers high. The formation of the Tharsis Bulge is so massive that geologists believe it actually shifted Mars's rotation axis. The sheer weight of the volcanic material redistributed enough mass to tilt the entire planet. There's also Valles Marineris, the canyon system that makes the Grand Canyon look like a crack in a sidewalk. 4,000 kilometers long, 200 kilometers wide in places, 7 kilometers deep. It stretches across a quarter of Mars's entire circumference. If you placed it on Earth, it would span the entire continental United States from New York to Los Angeles. And we still don't fully understand how it formed. The best current theory isn't erosion. It isn't a river. It's that the formation of the Tharsis Bulge created such enormous stress fractures in the Martian crust that the ground simply split. A tectonic crack the size of a continent. Mars is not dry. I want to be very clear about that. Because the image we have of Mars, a completely desiccated, waterless desert, is wrong. Water is still there, just not where you can see it. The polar ice caps, to start with the obvious. Both poles have permanent ice caps. The North Pole cap is mostly watery ice, under a thin seasonal layer of dry ice that comes and goes. The South Pole cap has watery ice too, buried beneath a thick layer of frozen carbon dioxide. The amount of water locked in those polar caps, if melted, would cover the entire surface of Mars to a depth of 35 meters. But that's not the surprising part. In 2018, a team using the Marsis radar on the Mars Express orbiter detected something beneath the South Polar ice cap. A highly reflective layer at a depth of about 1.5 kilometers. The kind of reflection that liquid water produces, not ice. Liquid water. Briny, hypersaline, possibly mixed with perchlorates, but liquid. A subglacial lake, like the ones we have under the ice in Antarctica. Since then, additional reflective layers have been detected. Multiple possible lakes. A potential system of liquid water bodies beneath the southern polar region. Now, let's be careful here. Not every scientist is convinced. The same reflections can theoretically be produced by certain types of ice or clay minerals. The debate is ongoing. But if those lakes are real, they would be the most habitable places on Mars today, because extremophile bacteria on Earth survive in very similar environments, in the subglacial lakes of Antarctica, in hypersaline pools, in environments with no sunlight, high radiation, and extreme cold. And there's more. In 2021, the InSight lander detected Marsquakes, actual seismic activity, suggesting the planet's interior is not completely dead. There is still heat, still geological movement, still energy, water plus heat plus chemistry. On Earth, that's a recipe we recognize. In February 2021, NASA landed the Perseverance rover inside Jezero crater, not a random location. Jezero was chosen specifically because it is an ancient river delta, a place where water once flowed into a lake and deposited sediment over millions of years. On Earth, river deltas are some of the most biologically rich environments that exist. Nutrients accumulate, organic material concentrates. If life ever existed on Mars, a delta like Jezero would be the place to look. Perseverance carries an instrument called Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals. It's specifically designed to detect organic molecules and biosignatures in rock samples. In 2022, Perseverance found organic molecules in Jezero crater, complex carbon-based compounds, in ancient sedimentary rock, in a former river delta. Now, let's be precise, because this is where the media coverage gets sloppy. Finding organic molecules does not mean finding life. Organic molecules can be produced by purely chemical processes with no biology involved. They arrive on asteroids. They form in ultraviolet-driven reactions in the atmosphere. They are common across the solar system. What matters is the context, and the context here is unusual. The specific types of organics found, their distribution within the rock, and their association with specific minerals suggests they weren't deposited by a meteorite. They appear to have formed in place, in the sedimentary environment, in the delta. Whether that formation involved biology or purely chemistry is a question Perseverance cannot answer alone. That answer will come when those rock samples, which Perseverance has been carefully sealed and stored, are returned to Earth. The Mars Sample Return mission, planned for the early 2030s, will bring those samples to laboratories where we can analyze them with instruments 10,000 times more sensitive than anything we can put on a rover. The samples are sitting there right now, on Mars, waiting. And then there's the thing all the media entirely missed. In late 2023, a study published in the journal Nature Geoscience reported something that should have been front-page news. The InSight lander, which operated on Mars until December 2022, had detected, through its seismic measurements, that Mars has not fully solidified, not completely dead, a liquid outer core. The same feature that Earth has, the same feature that drives Earth's magnetic field. The difference is that Mars's liquid core isn't generating a large-scale magnetic field right now. Probably because the conditions for the dynamo effect aren't quite right. The composition is different, the temperature gradients are different, but the liquid is there. And what that means, and why this is so important, is that our model of what killed Mars may be wrong, or at least incomplete. We assumed the core solidified, that the heat was gone, that Mars was, in every meaningful sense, a dead world below the surface. It isn't. There is still liquid iron in the interior of Mars, still heat, still movement, which means the story of Mars isn't over. It's just paused. And that raises a question that I think is the most interesting question in planetary science right now. Could a sufficiently large external energy input, say from massive asteroid impacts or from human-engineered processes, restart Mars's internal dynamo? Could we, theoretically, restart Mars's magnetic field? This isn't science fiction. It's a question geophysicists are now asking seriously. The Mars Sample Return mission will bring us rocks that may answer the life question once and for all. The rover will drill 2 meters below the Martian surface, deep enough to reach zones shielded from radiation where biological molecules could survive. We are closer to answering, was there life on Mars, than at any point in human history? And the answer, whatever it is, will be the most important scientific result of our lifetimes. Either Mars was barren, and we are alone in a way that should profoundly change how we treat the only living world we know, or Mars had life and died anyway, and we are living on a planet that is not as permanent as we like to think. Either way, it changes everything. Subscribe, hit the bell, tell me in the comments, do you think Mars had life? I'll read every single answer until the next mission. Jupiter is not a planet, not in the way you're thinking. It doesn't have a surface. It doesn't have ground. If you fell into Jupiter, you wouldn't land. You'd just sink. Deeper and deeper through layers of gas that become denser and hotter and stranger, until the pressure is so extreme that hydrogen stops being a gas and starts behaving like liquid metal. There is no bottom. But here's what nobody tells you about Jupiter. It is the reason you exist. Without Jupiter's gravitational influence in the early solar system, the asteroid and comet bombardment of the inner planets would have been catastrophic and unending. Life on Earth would never have had a chance to start, or it would have been wiped out before it could get anywhere. Jupiter is not just a big planet. It is the architect and the bodyguard of our entire solar system. And what the Juno spacecraft has found inside it in the last 8 years has changed almost everything we thought we knew. By the end of this video, I'll tell you about one specific Juno discovery that stunned the entire planetary science community. Something so unexpected that the researchers spent 2 years checking their data before they believed it. Let's go. Jupiter is not a planet, not in the way you're thinking. It doesn't have a surface. It doesn't have ground. If you fell into Jupiter, you wouldn't land. You'd just sink. Deeper and deeper through layers of gas that become denser, hotter, and stranger, until the pressure is so extreme that hydrogen stops being a gas and starts behaving like liquid metal. There is no bottom. Jupiter is, in the most literal sense, a different kind of world, not a rocky body orbiting the sun, a failed star, a colossal sphere of mostly hydrogen and helium held together by its own gravity, generating more heat than it receives from the sun, with a magnetic field 14 times stronger than Earth's, and a storm system larger than our entire planet that has been spinning for at least 350 years. It contains more mass than all the other planets in the solar system combined, twice over. And it is, in ways most people have never considered, the reason life exists on Earth. Today we're going through everything. What Jupiter actually is below those cloud bands, what the Great Red Spot really is, and why it's dying, how Jupiter shaped and continues to protect our solar system, what its moons hide, and the one discovery from the Juno mission that the scientific community is still trying to fully explain. This is the planet that runs everything, and you've been underestimating it. Let's go beneath the clouds, because what's down there is genuinely strange. The top layer you can see, the cloud bands, are made of ammonia ice crystals. The bright zones and dark belts are the result of Jupiter's incredibly fast rotation. One full rotation every 10 hours. The fastest rotation of any planet in the solar system. That spin stretches the atmosphere into those parallel bands, with rising and sinking gas creating the light and dark pattern we see. Below the ammonia cloud layer, temperatures and pressures climb rapidly. Water ice clouds, then water droplets, then something that isn't quite gas and isn't quite liquid, a region of supercritical hydrogen where the distinction between gas and liquid loses its meaning. Go deeper still, roughly 20,000 kilometers below the cloud tops, and something extraordinary happens. The pressure reaches 3 million times Earth's atmospheric pressure. At that point, hydrogen undergoes a phase transition. The electrons are stripped from the hydrogen atoms and move freely through the fluid. Hydrogen becomes electrically conductive. It flows like a metal, metallic hydrogen. A state of matter that we can only create on Earth for tiny fractions of a second in laboratory experiments. On Jupiter, there's an ocean of it, tens of thousands of kilometers deep. That ocean of metallic hydrogen, churning under Jupiter's rapid rotation, is what generates its magnetic field. The most powerful planetary magnetic field in the solar system, so strong that it extends 5 million kilometers toward the Sun and 700 million kilometers in the opposite direction. If you could see Jupiter's magnetic field with your eyes, it would appear larger than the full moon in our sky. And at the very center of Jupiter, we still don't know for certain. The Juno mission has given us strong evidence of a fuzzy, diffuse core, not the compact rocky ball models predicted, but something more like a dissolved, mixed region where heavy elements are blended into the surrounding hydrogen. An inside-out core. A core that may extend halfway to the surface. Nobody predicted that. Wait, because there's more. Scientists also discovered that it might rain diamonds inside Jupiter. Lightning in the upper atmosphere converts methane into soot. That soot falls as carbon particles, compressing under the extreme pressure as it sinks. At the right depth, around 30,000 kilometers down, the pressure and temperature are exactly right to turn carbon into diamond crystals. Diamonds falling as rain. Millions of tons of them per year. Deeper still, they melt into liquid diamond oceans. Jupiter rains diamonds. And that's still not the most surprising thing we've found. The Great Red Spot has been observed continuously since 1830. But historical records suggest it may have been there since the 1600s. That means there has been a storm on Jupiter, a single, continuous, unbroken storm, for somewhere between 350 and 400 years. Let's talk about what that storm actually is. The Great Red Spot is a high-pressure anticyclone, a region where winds spiral upward around a high-pressure center. On Earth, anticyclones produce calm, clear weather. On Jupiter, the same physics produces a storm that currently spans about 16,000 kilometers from edge to edge. That's wider than the entire Earth. Wind speeds at the outer edge, 430 to 680 kilometers per hour. The red color, which has puzzled scientists for decades, is now thought to come from complex organic molecules and sulfur compounds that are lofted to the top of the storm's cloud column, where ultraviolet radiation from the sun triggers chemical reactions that produce red-colored compounds. Jupiter is making its own chemistry at the top of a storm that's been running for centuries. But here's the thing nobody wants to say out loud. It's shrinking. In the 1800s, the Great Red Spot was estimated to be 40,000 kilometers across, nearly 4 times the diameter of Earth. Today, it's about 16,000 kilometers, and shrinking by roughly 900 kilometers per year. At that rate, it will become circular, losing its distinctive oval shape within the next decade or two. And at some point after that, based on current projections, it may disappear entirely. The greatest storm in the solar system, hundreds of years old, shrinking. Why? The honest answer is that we're not entirely sure. The leading theory is that smaller storms, called ovals, that feed energy into the Great Red Spot have been decreasing in number. The GRS is running out of fuel. There's also evidence it's getting taller as it shrinks, like a spinning top that wobbles as it slows. The storm is becoming more circular, more compact, and, counterintuitively, more intense at its core, even as the overall size decreases. It's going out with a fight. Juno has flown directly over the Great Red Spot multiple times. What it found beneath it, how deep the storm actually goes, was one of the biggest surprises of the entire mission. Scientists expected a shallow atmospheric phenomenon, a weather system basically. The Great Red Spot's roots extend at least 500 kilometers deep into Jupiter's atmosphere. 500 kilometers. Most of Earth's atmosphere is less than 50 kilometers thick. It's not a weather system. It's a geological feature of the atmosphere. Jupiter is not just a planet, it's a gravitational machine. And it has been shaping our solar system since before Earth existed. In the early solar system, the region beyond Mars was full of material, rocks, ices, planetesimals, that never coalesced into a planet because Jupiter's gravity constantly disrupted them. That region became the asteroid belt, not because the material ran out, but because Jupiter kept stirring it up, preventing it from accumulating. Jupiter essentially vetoed the formation of another planet between Mars and itself. But its influence goes further, much further. The Grand Tack hypothesis, one of the most widely discussed models of early solar system evolution, proposes that Jupiter didn't always sit where it does now. In the first few million years after the Sun's formation, Jupiter migrated inward toward the Sun, almost reaching where Mars is today. Then Saturn formed, locked into a gravitational resonance with Jupiter, and the two giant planets migrated back outward together. This inward and outward migration, the Grand Tack, sculpted the inner solar system. It cleared out most of the material that might otherwise have built larger rocky planets. It's one reason Mars is so small, and it's part of why Earth ended up with just the right amount of water, some delivered by asteroids whose orbits were perturbed by Jupiter during its migration. Jupiter delivered water to Earth, and it continues to protect us today. The Shoemaker-Levy 9 comet. In 1994, this comet broke apart and slammed into Jupiter over the course of 6 days. 21 separate impact fragments. The largest impact flash was larger than Earth. The collision left dark scars in Jupiter's atmosphere that lasted for months. If that comet had not been captured and destroyed by Jupiter, its trajectory put it on a potential path toward the inner solar system. Jupiter intercepted it. Jupiter does this constantly. Its gravitational influence deflects and captures comets and asteroids that would otherwise enter the inner solar system. It acts as a shield, imperfect, not absolute, but real. Models of solar systems without a Jupiter-like gas giant show inner planets suffering bombardment rates 10 to 20 times higher than what Earth experiences. Without Jupiter, Earth gets hit, repeatedly, catastrophically, frequently enough that complex life probably never gets the time it needs to develop. You are alive, in part, because Jupiter exists. That's not poetic exaggeration. That's orbital mechanics. Galileo Galilei discovered them in 1610 with a crude telescope. 4 moons: Io, Europa, Ganymede, Callisto. He called them the Medicean stars, a flattery to his patrons. We call them the Galilean moons, and they are, individually, more scientifically interesting than most planets. Io is the most volcanically active body in the entire solar system, more active than Earth. Hundreds of volcanoes, lava lakes, sulfur eruptions that reach 300 kilometers into space. The reason? Gravitational tidal forces from Jupiter, Europa, and Ganymede constantly flex and squeeze Io's interior, generating enormous heat. Io is literally being kneaded like dough by the gravity of its neighbors. Its surface is so geologically young that there are almost no impact craters. They're constantly erased by fresh volcanic material. Ganymede is the largest moon in the solar system, larger than the planet Mercury. It is the only moon with its own magnetic field. It likely has a subsurface ocean of salt water sandwiched between layers of ice, an ocean containing more water than all of Earth's oceans combined. The JUICE mission, currently en route from ESA, will orbit Ganymede starting in 2034. Callisto is the most heavily cratered object in the solar system, a geological museum, virtually unchanged for 4 billion years, its surface a perfect record of every impact since the solar system formed. And then there is Europa. Europa deserves its own section, because Europa might be the most important world in the solar system, after Earth. And what we found there is the reason 3 separate space agencies are sending spacecraft there in this decade. Europa is slightly smaller than our moon. From a distance, it looks like a cracked billiard ball, smooth, white-blue, covered in a network of reddish-brown lines that crisscross the entire surface. Those lines are fractures, cracks in the ice, and beneath that ice, between 10 and 30 kilometers thick, there is a liquid water ocean. We know this. This is not speculation. Magnetic field measurements from the Galileo spacecraft in the 1990s detected an induced magnetic field around Europa, the signature of a conducting fluid, likely salt water, responding to Jupiter's powerful magnetic field. The subsurface ocean of Europa is essentially confirmed. The ocean is estimated to be around 100 kilometers deep. It contains roughly twice the volume of all Earth's oceans combined. And it has been liquid for billions of years, kept warm not by proximity to the sun, but by the same tidal flexing that heats Io, tidal heating. Jupiter's gravity squeezes Europa continuously, generating internal heat. That heat keeps the ocean liquid even though Europa's surface is at minus 160 degrees Celsius. And here's what makes astrobiologists genuinely excited. On Earth, life doesn't need sunlight. We have discovered entire ecosystems around hydrothermal vents on the ocean floor, kilometers beneath the surface, in absolute darkness, where the energy comes not from photosynthesis, but from the chemical reactions between hot volcanic water and rock. Europa almost certainly has a rocky seafloor. It almost certainly has hydrothermal activity. Tidal heating generates heat that must go somewhere, and at the seafloor, that heat produces the same chemistry as Earth's hydrothermal vents: liquid water, chemical energy, rocky interface, billions of years of stability. On Earth, that combination produced life. The Europa Clipper mission, launched by NASA in October 2024, will arrive at Jupiter in 2030 and perform around 50 flybys of Europa. It will measure the ice thickness, map the ocean's chemistry using plumes of material that Europa's interior vents into space, and search for biosignatures in those plumes. It will not land. It will not drill through the ice. But it will tell us definitively whether Europa's ocean has the right chemistry to support life. And if the answer is yes, the next mission will land and drill. We may be less than 20 years from knowing whether life exists in that ocean. The Juno spacecraft has been orbiting Jupiter since July 2016. It was designed to peer beneath the clouds and answer fundamental questions about Jupiter's interior, its magnetic field, and its water content. And it has delivered extraordinary results. But the result nobody was ready for came in 2021. Juno's instruments detected something remarkable at Jupiter's poles. Not the banded atmosphere of the equatorial and mid-latitude regions, the famous stripes everyone knows. At the poles, the atmosphere is completely different, chaotic, turbulent, and organized not into bands, but into clusters of enormous cyclones. At the North Pole, one central cyclone surrounded by 8 others arranged in a perfect octagonal pattern. At the South Pole, one central cyclone surrounded by 5, arranged in a pentagonal pattern. Polygonal arrangements of cyclones, self-organized, stable, persisting for years. Nothing in our models of atmospheric dynamics predicted this. The stability of these formations, why they don't merge into each other, why they maintain their geometric pattern, is still an active area of research. The best current explanation involves a balance between the vortice's tendency to drift toward the pole and the restoring force that pushes them back, locking them into a geometric equilibrium. But we don't fully understand it yet. Jupiter, the planet we thought we knew best because we could see its surface from Earth, is still producing surprises. After 8 years of continuous observation, after more than 50 close passes, after mapping its magnetic field, its atmospheric chemistry, its interior structure, it still surprises us. The extended Juno mission is now exploring the Galilean moons directly. It has completed flybys of Ganymede, Europa, and Io, sending back the highest resolution images of these moons ever captured. The JUICE mission from ESA, launched in April 2023, is currently traveling to the Jupiter system and will enter orbit around Ganymede in 2034. The Europa Clipper arrives in 2030. In the next 10 years, the Jupiter system will be the most intensively studied region of the outer solar system in history. And if Europa Clipper finds the right chemistry in those ocean plumes, the building blocks of life in a liquid water environment, then the mission that follows will change everything. Not just our understanding of Jupiter, our understanding of what life is, where it can exist, how common it might be. Jupiter is not just a planet. It is the key to the most important question humanity has ever asked. Subscribe, hit the bell, and tell me in the comments, do you think we'll find life in Europa's ocean? Because I think about that question every single day. Until the next mission. Saturn's rings are disappearing, right now, today, as you watch this video. They're being pulled into Saturn's atmosphere by gravity, what scientists call ring rain, at a rate of roughly 10,000 kilograms per second. 10,000 kilograms, every second. At that rate, the rings will be completely gone within 100 million years. That sounds like a long time. But the solar system is 4.5 billion years old. On that scale, 100 million years is nothing. We are catching Saturn in what may be the last 2% of its ringed existence. And here's what makes this genuinely unsettling. The rings aren't ancient, they're young. Astronomers now believe they formed somewhere between 10 and 400 million years ago. which means they appeared around the time dinosaurs were walking the Earth. Saturn didn't always look like Saturn, and soon, again, cosmically speaking, it won't look like this again. But the rings are only the beginning of what makes this planet strange. By the end of this video, I'll tell you about a discovery on one of Saturn's moons that has forced scientists to completely rewrite the rulebook on where life can exist. Let's start. Saturn is the most beautiful planet in the solar system. Everyone agrees on that. The rings, the golden atmosphere, the perfect geometry of it all. When Galileo first saw Saturn through his telescope in 1610, he didn't understand what he was seeing. He thought it was 3 planets, a large one with 2 smaller ones on either side. His telescope wasn't powerful enough to resolve the rings. It took another 50 years and a better telescope before Christian Huygens figured it out. A ring, a single, thin, flat ring surrounding the planet, separate from it, not touching. The discovery stunned the scientific world. Nothing like it had ever been seen. Nothing like it exists anywhere else in the solar system with the same visual drama. But here's what Saturn has been hiding behind those rings. It is the least dense planet in the solar system. Its average density is 0.687 grams per cubic centimeter. Water has a density of 1.0, which means if you could find a bathtub large enough, Saturn would float. It has a storm at its north pole that is shaped like a perfect hexagon, 30,000 kilometers across, and has been stable for decades. Nothing in atmospheric physics fully explains why it's a hexagon. One of its moons shoots liquid water hundreds of kilometers into space. Another has a complete weather cycle, rain, rivers, lakes, and seas, but made entirely of liquid methane instead of water. And its rings, the most iconic feature in the entire solar system, are disappearing. Saturn is not what you think. Let's go beneath the beauty. Saturn is a gas giant, like Jupiter, but with crucial differences. Its mass is about 95 times that of Earth, but its volume is enormous. Roughly 764 Earths could fit inside. And most of that volume is almost nothing. Hydrogen and helium in their lowest density forms. At the cloud tops, you'd find ammonia ice crystals, similar to Jupiter. But Saturn's atmosphere is noticeably calmer than Jupiter's. The bands are more muted, the colors less saturated. Pale gold, cream, faint amber. Saturn looks quieter. It isn't. Wind speeds at Saturn's equator reach 1,800 kilometers per hour, nearly 5 times the speed of sound on Earth. The calmness is an illusion. The atmosphere is simply too thick and uniform to show the turbulence clearly from the outside. Below the cloud layers, the structure mirrors Jupiter, molecular hydrogen giving way to metallic hydrogen as the pressure climbs. But Saturn has less mass pressing down, so the metallic hydrogen zone begins deeper and is less extreme. At the very center, a rocky and icy core, estimated at 9 to 22 times the mass of Earth. And here's where Cassini changed everything we thought we understood. Using a technique called ring seismology, essentially listening to how Saturn's gravitational vibrations disturb the ring particles, the way seismologists listen to how earthquakes propagate through Earth. Scientists discovered that Saturn's core is not compact and solid. It is fuzzy, diffuse, extended, a soup of rock, ice, and hydrogen that gradually transitions into the surrounding gas without a clear boundary. The core of Saturn may extend 60% of the way to the surface. Sound familiar? Jupiter has the same thing. 2 gas giants. both with dissolved, diffuse, extended cores. Neither matching our previous models. The interiors of giant planets are telling us something about planetary formation that we clearly didn't understand before Cassini and Juno arrived, and we're still working out what that something is. But what makes Saturn truly unique in the solar system isn't its interior, it's what's around it. Saturn's rings are not solid. They look like flat disks from a distance. But they are made of billions of individual particles, chunks of water ice ranging from microscopic grains to house-sized boulders, all orbiting Saturn at different speeds in an almost perfectly flat plane. The ring system stretches about 282,000 kilometers from end to end, but its thickness? In most places, less than a kilometer. Some sections are only 10 meters thick. Think about that. A structure wider than the distance from Earth to the Moon, 10 meters thick. The proportional thinness of Saturn's rings, relative to their width, is greater than a sheet of paper, and they are not a single ring. The main rings, labeled A, B, C, and D from outside in, are separated by gaps. The largest gap, the Cassini division, is 4,800 kilometers wide. It looks empty. It isn't. It contains thin, dusty material. But it's dramatically less dense than the main rings because orbital resonance with the moon mimas has swept most particles out. Shepherd moons maintain the ring edges, tiny moons embedded within or just outside the rings, their gravity herding the ring particles into precise boundaries. The B ring alone contains more material than the moon mimas. The entire ring system contains enough mass to build a small moon. Now, where did they come from? For decades, scientists assumed the rings were ancient, formed at the same time as Saturn, 4.5 billion years ago. Cassini proved they are not. By measuring the rate at which the rings are absorbing dust from meteorite impacts, and comparing the current dust load to what it should be if the rings were ancient, scientists calculated the rings are between 10 and 400 million years ago. Young, cosmically brand new. The leading theory for their origin, a moon of Saturn, perhaps the size of Titan, drifted too close to Saturn due to gravitational interactions. It crossed what's called the Roche limit, the point at which tidal forces overcome the moon's own gravity. It was torn apart. The debris spread into a ring. A moon died to make the rings, and the rings are now dying in turn. Ring rain. The particles at the inner edge of the rings are electrically charged by ultraviolet radiation and the solar wind. That charge connects them to Saturn's magnetic field lines, which pull them down into the atmosphere. 10,000 kilograms of ring material per second raining into Saturn. At that rate, without replenishment, the rings will be gone within 100 million years. We are watching the rings of Saturn in their final era. The most iconic image in astronomy is temporary, and we happen to be alive to see it. At Saturn's North Pole, there is a storm. Not a circular storm like the Great Red Spot on Jupiter. Not a chaotic swirl of competing weather systems. A hexagon. A perfect six-sided geometric shape, each side measuring approximately 14,500 kilometers, larger than Earth's diameter. The entire hexagonal storm system rotates as a unit. It has been there since we first observed it with Voyager 2 in 1981. 40-plus years of observation, perfectly stable, perfectly hexagonal. How does a storm form a hexagon? In nature? In a gas giant atmosphere? The answer involves fluid dynamics. When a circular jet stream, a fast-moving wind current, encounters waves in a slower surrounding atmosphere, under the right conditions, the interaction can create polygon shapes. The number of sides depends on the wind speed ratio between the fast jet and the slower surrounding atmosphere. Scientists have reproduced hexagonal patterns in laboratory tanks of rotating fluid. The physics works. But why Saturn's polar jet produces a hexagon specifically, rather than a pentagon or an octagon, is still not fully constrained by the models. And then there's what's inside the hexagon. At the very center, a polar vortex, a circular storm at the eye of the hexagon, about 2,000 kilometers wide, with 150-meter-per-hour winds at its edge and a clear eye at the center, like a hurricane, but larger than the entire continental United States. The hexagon rotates around this central vortex. The vortex rotates inside the hexagon. Both maintain their structure indefinitely. Cassini photographed the hexagon in multiple wavelengths over years of continuous observation. And in 2018, something changed. Cassini's final images showed the hexagon had changed color. From the blue-gray it had appeared in earlier mission images, it had turned golden yellow. The cause, seasonal change. As Saturn moved through its 29-year orbit and the North Pole received more sunlight, photochemical reactions in the atmosphere changed the composition and color of the haze. Even the hexagon has seasons. A perfect geometric storm, big enough to swallow Earth, changing color with the Saturnian seasons. And still, nobody fully understands why it's a hexagon. In 2005, the Cassini spacecraft was flying past a tiny moon of Saturn, just 504 kilometers across, barely visible from Earth, when its instruments detected something extraordinary: water vapor and ice particles shooting out of the South Pole, geysers, on a moon of Saturn. The moon is Enceladus. And what Cassini found there, over the following decade of close observation, is arguably the most important discovery in the history of planetary exploration. Enceladus has a global subsurface ocean of liquid water beneath its icy shell. Not a theoretical inference, not an indirect measurement. Cassini flew directly through the plumes erupting from the South Pole, through the actual material coming out of the interior, and analyzed it directly. The results: water, salt, silica particles, indicating hydrothermal activity on the seafloor, organic molecules, molecular hydrogen, produced by the reaction between hot water and rock, carbon dioxide, methane. Every single one of those components, when found together in a liquid water environment, is associated on Earth with the conditions that support microbial life. Every single one. The silica particles were particularly significant. On Earth, silica particles of the specific size Cassini detected in the plumes only form in hydrothermal vent environments where water is heated to at least 90 degrees Celsius and interacts with silicate rock at high pressure. Enceladus has hydrothermal vents on its seafloor, hot water interacting with rock, in a liquid water ocean, under ice, on a moon of Saturn, 1.4 billion kilometers from the Sun. The tidal heating from Saturn, the same gravitational kneading that keeps Io volcanic, keeps Enceladus's ocean liquid and its vents active. And in 2023, a reanalysis of Cassini data found phosphorus in the plumes. Phosphorus, one of the 6 essential elements for life as we know it. The last of the 6 to be confirmed at Enceladus. All 6 chemical building blocks of life, confirmed in the plumes of a moon of Saturn. Enceladus is, as of right now, the most promising place to search for extraterrestrial life in the solar system. More promising than Mars, more accessible than Europa, because its ocean is actively venting material into space. We don't need to land and drill. We just need to fly through the plumes and catch what's already coming out. And that is exactly what the next mission will attempt. Titan is Saturn's largest moon, and it is, without question, the most Earth-like world in the solar system, other than Earth itself. It has a thick atmosphere, denser than Earth's, in fact. Surface pressure about 1.5 times greater than what we breathe. Nitrogen-dominated, just like Earth's, with an orange photochemical haze so thick that the Voyager probes couldn't see the surface at all. It has weather, real weather, clouds that form and dissipate, rain, seasons that change over its 29-year orbit of Saturn, wind-driven dunes covering vast equatorial regions. It has rivers, carved channels visible from orbit, their branching patterns unmistakable. These are drainage networks, formed by liquid flowing downhill over geological time. It has lakes and seas, collected at the poles. The largest, Kraken Mare, is larger than the Caspian Sea. Everything I've just described sounds like Earth, but none of it involves water. Titan is too cold for liquid water. Its surface temperature is minus 179 degrees Celsius. On Titan, water is rock, frozen solid, forming the bedrock of mountains and riverbeds. What flows on Titan is liquid methane and ethane. The rain is methane. The rivers are methane. The lakes and seas are liquid hydrocarbons. Titan has a complete methane cycle. Methane evaporates from the surface, rises into the atmosphere, condenses into clouds, rains back down, collects in lakes, flows through rivers to the seas, exactly like Earth's water cycle, but with a completely different molecule. And beneath the surface, like Enceladus, there may be a subsurface liquid water ocean, kept warm by internal heat and tidal forces. So Titan potentially has two completely different environments where life might exist. On the surface, exotic chemistry in liquid methane, potentially supporting life forms with completely different biochemistry than anything on Earth. And underground, a liquid water ocean where conventional life as we know it might survive. Two possible biospheres on a single moon. The Dragonfly mission, a nuclear-powered rotorcraft, will arrive on Titan in 2034. It will fly from location to location on Titan's surface. No rover could traverse the terrain, sampling different environments. River sediments, impact crater interiors where water ice and organic material were briefly mixed by the heat of impact. The organic dunes. If there is life on Titan, surface life, exotic life, Dragonfly will find its chemical fingerprints. On September 15, 2017, the Cassini spacecraft, after 13 years in orbit around Saturn, performed what NASA called the grand finale. Running low on fuel, with the mission coming to its end, the team made a deliberate choice. Rather than risk Cassini drifting and potentially contaminating Enceladus or Titan with Earth microbes, however unlikely, they plunged the spacecraft into Saturn's atmosphere. 22 times in its final months, Cassini dove between Saturn and its innermost ring, a gap less than 2,000 kilometers wide, a region no spacecraft had ever entered. And in those final dives, it made its most surprising discovery. The gap between Saturn and its rings is not empty. It contains complex organic molecules, not simple compounds. Complex large organic molecules raining down from the rings into Saturn's atmosphere, or wafting up from the atmosphere into the ring region. The chemistry between Saturn and its rings is active, dynamic, molecules moving in both directions. This was the last thing Cassini sent home before it burned up in Saturn's atmosphere. a confirmation that the rings and the planet are chemically connected, that the boundary between planet and ring system is not a dead vacuum, but a chemically active exchange zone. We lost Cassini at 7:55 a.m. Pacific Time on September 15, 2017. The signal simply stopped. The spacecraft was gone, consumed by the planet it had spent 13 years studying. It left behind more than 600 gigabytes of scientific data. Data that scientists are still analyzing today. Data that produced the Enceladus ocean discovery, the ring age calculation, the fuzzy core finding, the hexagon seasonal color change. And the data from those final grand finale dives is still being fully processed. Before 2035, the Dragonfly mission will land on Titan. An Enceladus orbiter and lander mission, currently in early planning at NASA and ESA, may follow in the late 2030s. The questions Cassini raised: can life exist in Enceladus's ocean? Can exotic life exist in Titan's methane seas? Will be answered within the lifetimes of most people watching this video. Saturn taught us that the most beautiful thing in the solar system is also one of the most scientifically consequential. That the rings we admired for 4 centuries are young and temporary. That its moons are more interesting than the planet itself. And that the boundary between life and no life may be much more flexible than we ever assumed. Cassini changed everything, and what comes next might change it again. Subscribe, hit the bell, and tell me in the comments, Enceladus or Titan? Which world do you think is more likely to have life? I genuinely don't know the answer, and I love that. Until the next mission. Uranus is the only planet in the solar system that rotates on its side. Its axis is tilted 98 degrees, not slightly, not a bit off-center. It is essentially lying down. It rolls around the sun like a bowling ball, its poles pointing roughly toward the sun instead of perpendicular to it. Something hit Uranus, something enormous, and the impact was violent enough to permanently knock the entire planet over. We've known about the tilt for centuries. What we've been arguing about, and what a 2023 computer simulation finally shed new light on, is exactly what hit it, and whether that collision also explains the other mysteries. Because Uranus has a lot of mysteries. It is colder than Neptune, despite being closer to the sun. Its magnetic field points in the wrong direction, at the wrong angle, from the wrong place. It has rings that nobody expected, and moons that, as of 2023, appear to have active subsurface oceans that nobody predicted. Uranus is the most scientifically neglected planet in our solar system. 1 spacecraft, 1 flyby, 6 hours, in 1986. Everything we know about Uranus comes from 6 hours of data collected 40 years ago. And it's already full of things we can't explain. Let's fix that. In January 1986, the Voyager 2 spacecraft flew past Uranus. It was the only spacecraft that ever has. It spent 6 hours in the Uranian system, flying past a pale blue-green sphere at 64,000 kilometers per hour, its instruments scanning frantically, collecting everything they could in the brief window of close approach. Then it kept going, toward Neptune, toward interstellar space. That was 40 years ago. In the 4 decades since, no other spacecraft has visited Uranus. No orbiter, no probe, no lander, nothing. Every other planet in the solar system has received multiple missions since 1986. Mars has had rovers, landers, orbiters, and helicopters. Jupiter has had Galileo and Juno. Saturn had Cassini for 13 years. Even tiny Pluto got a flyby in 2015. Uranus has had 6 hours. And in those 6 hours, and in the decades of Earth-based observation and computer modeling that followed, we found a world so strange, so anomalous, so full of contradictions that planetary scientists have been arguing about it ever since. It rotates on its side. It's colder than it should be. Its magnetic field makes no sense. It has rings nobody expected. And as of 2023, its moons may be hiding oceans. Uranus is not a boring, featureless ice ball that deserves its place at the back of the solar system family photo. It is the most misunderstood planet we have, and we are long overdue for a proper introduction. Let's start with a classification problem. Uranus is almost always grouped with Jupiter and Saturn as a gas giant. It isn't one. Uranus, along with Neptune, belongs to a separate category, ice giants. And the difference matters enormously. Jupiter and Saturn are predominantly hydrogen and helium. Their interiors are dense, hot, and metallic. Their atmospheres grade smoothly into their interiors. Uranus is different. Its bulk composition is dominated by what planetary scientists call ices. Not frozen water alone, but a mixture of water, ammonia, and methane in a hot, dense, supercritical fluid state. Not actually frozen. The word ice here refers to the chemical composition, not the physical state. This fluid, hot, pressurized, electrically conducting in places, makes up the vast majority of Uranus's interior, below a relatively thin hydrogen-helium atmosphere, above a small rocky core. The atmosphere itself is what gives Uranus its color. Methane in the upper atmosphere absorbs red light and reflects blue and green wavelengths. The result is that unmistakable pale cyan-teal color, one of the most distinctive in the solar system. But here's what most people don't know about Uranus's appearance. It's almost completely featureless. When Voyager 2 flew past, it photographed a smooth, nearly banded, structureless sphere. Where Jupiter has violent storms and Saturn has subtle bands and the hexagon, Uranus presented what appeared to be a blank canvas. Scientists nicknamed it the bowling ball. That apparent featurelessness is itself a mystery. Neptune, almost identical in composition and size, has visible storms, dark spots, and dynamic atmospheric activity. Why does Uranus look dead when Neptune looks alive? The answer connects directly to the strangest fact about Uranus, the one that makes it unique in the entire solar system: its internal heat. Uranus's axial tilt of 98 degrees is not natural. No planet forms tilted like that. The protoplanetary disk from which planets form is flat. Planets form rotating upright or close to it. Small tilts can develop over time through gravitational interactions. But 98 degrees, something hit it. The question has always been, what exactly, and when? For decades, the leading hypothesis was a single massive impact. One large protoplanet, roughly Earth-sized or larger, slamming into the young Uranus billions of years ago with enough momentum to tilt its entire rotation axis. Simple, clean, explains the tilt, but it creates a problem. If a single massive impactor hit Uranus and transferred that much angular momentum, the collision would also have generated enormous heat. Heat that should have persisted for billions of years. Heat that Uranus should still be radiating today. But Uranus radiates almost no heat. Its internal temperature is nearly the same as its surface temperature. The heat that should be there isn't. A 2018 study proposed a solution. The impactor wasn't a single rocky body. It was an ice-rich body, a large protoplanet, or planetesimal, composed largely of ices, that hit at a relatively low velocity and a glancing angle. A slow, icy, sideways hit. That kind of impact could tilt the axis without generating the same catastrophic heat surge. The ice-rich impactor would have mixed into Uranus's interior, potentially creating a thermal barrier, a layer that traps the planet's internal heat and prevents it from radiating outward. Effectively, the collision that knocked Uranus over also insulated it, buried its heat under a chemical blanket, and a 2023 computer simulation went further. It modeled the collision in unprecedented detail and found that a single impactor may not be enough. The current distribution of Uranus's moons, their tilts, their orbits, their composition, is best explained by a series of smaller impacts rather than one giant one. Multiple collisions, a violent early history, each one adding to the tilt, reshaping the moon system, adding to the thermal insulation. Uranus didn't have one bad day, it had many, and it has never recovered. Here is something that should not be true. Uranus is the coldest planet in the solar system, not Neptune. Uranus. Neptune is almost 1 billion kilometers further from the Sun than Uranus. By every reasonable calculation, it should be the colder of the two. It isn't. Neptune's minimum atmospheric temperature, -218 degrees Celsius. Uranus's minimum atmospheric temperature, -224 degrees Celsius. Uranus, the closer planet, is colder. Every other planet in the solar system radiates more heat than it receives from the Sun. Their interiors are warm, remnants of the heat generated during their formation, or produced by radioactive decay, or generated by gravitational compression. That internal heat leaks outward and warms the atmosphere. Jupiter radiates 1.7 times more energy than it receives from the Sun. Saturn radiates 1.8 times more. Neptune radiates 2.6 times more. Uranus radiates essentially the same energy it receives. Its internal heat output is close to zero. Something is blocking it. The leading explanation connects directly to the collision. The impact that tilted Uranus, particularly if it involved an ice-rich body mixing into the interior, may have created a stable layered structure inside the planet. A thermal stratification, a chemical boundary layer that acts like insulation, trapping the internal heat and preventing it from reaching the surface. Think of it like a thermos flask. The heat is in there. It just can't get out. If this is correct, the interior of Uranus may be significantly warmer than we can measure from outside. The internal heat that should have dissipated over 4.5 billion years is still trapped, still locked inside, which means Uranus is not a cold, dead world. It's a world with a fever it can't break. And that trapped heat changes how we think about everything inside it, including the diamonds. Every planet with a magnetic field generates it the same basic way. A conducting fluid, molten iron, metallic hydrogen, circulating in the interior. The circulation creates electrical currents. The electrical currents generate a magnetic field. The magnetic field is roughly aligned with the planet's rotation axis. Roughly, Earth's magnetic pole is about 11 degrees off from its geographic pole. Jupiter's is about 10 degrees. Saturn's is almost perfectly aligned. Uranus's magnetic field is offset from its rotation axis by 59 degrees. That's not a small misalignment. That's a completely different geometry. The magnetic north pole of Uranus is not near either geographic pole. It's somewhere in the middle latitudes. But it gets stranger. The magnetic field doesn't even originate from the center of the planet. It's offset from the planet's center by about 1/3 of the planet's radius. Off-center, asymmetric, pointing sideways relative to where it should be. The result: Uranus has the most chaotic, lopsided, asymmetric magnetic field of any planet in the solar system. As the planet rotates, the magnetic field wobbles wildly. Its strength varies enormously depending on where you are on the planet's surface, by a factor of up to 10 between the weakest and strongest points. Why? Almost certainly because the magnetic field isn't being generated in a metallic core, like Earth's, but in the electrically conducting icy fluid of the interior. Liquid water, ammonia, and methane under pressure can conduct electricity, and the chaotic convection patterns in that fluid create a chaotic magnetic field. Neptune has a similarly chaotic magnetic field, supporting the idea that this is a property of ice giants in general. And that same interior, the hot, pressurized, ice-rich fluid, is where something spectacular may be happening. Diamond rain. At depths of about 8,000 kilometers inside Uranus, where pressures reach millions of atmospheres and temperatures hit thousands of degrees, methane breaks down under the extreme conditions. Its carbon atoms separate from the hydrogen, and that carbon, under those pressures, crystallizes into diamonds. Diamonds form and sink through the fluid interior of Uranus, accumulating at depth, potentially forming a diamond layer around the core. Laboratory experiments at Lawrence Livermore National Laboratory have reproduced this process, firing lasers at plastic samples to simulate the conditions inside ice giants and watching diamond crystals form in real time. Uranus almost certainly contains diamonds, billions of tons of them, falling like snow through the interior of the most overlooked planet in the solar system. Uranus has 27 known moons, all named after characters from Shakespeare and Alexander Pope. Most of them are small, dark, unremarkable. Rocky bodies captured early in the solar system's history. But 5 of them, Miranda, Ariel, Umbriel, Titania, and Oberon, are large enough to be spherical, large enough to have undergone geological processing, large enough to potentially have interesting interiors. For decades, they were assumed to be cold and geologically dead. The Voyager 2 flyby showed heavily cratered, relatively featureless surfaces. Case closed. Boring moons. In 2023, a team of researchers reanalyzed Voyager 2's 40-year-old infrared data using modern analysis techniques that didn't exist when the data was first collected. What they found was not expected. 4 of the 5 large moons, Ariel, Umbriel, Titania, and Oberon, show thermal signatures consistent with active internal heat. Heat that can't be explained by radioactive decay alone. Heat that suggests something more dynamic is going on inside. The most likely explanation: subsurface oceans of liquid water. Maintained by tidal heating, the same mechanism that keeps Europa and Enceladus liquid, and possibly by the heat trapped in the moon's interiors. Ariel in particular shows surface features, fractures, smooth plains, resurfaced regions that on any other moon would immediately suggest cryovolcanism, material from a liquid interior erupting onto the surface and freezing. If Ariel has a subsurface ocean, then Uranus has not 1 but potentially 4 worlds with liquid water, 4 potential habitats for life, around a planet we visited for 6 hours 40 years ago and then ignored. This single 2023 reanalysis completely transformed the scientific case for a Uranus mission. Suddenly, Uranus isn't just a tilted curiosity. It's potentially the most life-rich system in the outer solar system. In April 2022, the National Academies of Sciences published the Planetary Science and Astrobiology Decadal Survey, the document that sets NASA's priorities for the next decade of planetary exploration. For the first time in history, the top priority flagship mission was not Mars. It was not Europa. It was Uranus. The Uranus Orbiter and Probe, UOP, was ranked as the single highest priority large mission for the coming decade, above everything else. The scientific case had become overwhelming. An ice giant with a dramatic tilt, a missing heat source, a chaotic magnetic field, potential diamond interiors, and up to 4 moons that may harbor subsurface liquid water. All of it understood from 6 hours of data collected 40 years ago with 1980s technology. The UOP mission concept involves an orbiter that would spend several years in the Uranian system. Not a flyby, but a true orbital mission, the equivalent of what Cassini did for Saturn, and an atmospheric probe that would plunge into Uranus's atmosphere and measure its composition directly. The atmospheric probe is particularly important. The composition of Uranus's interior, the ratio of water to ammonia to methane, the distribution of heavier elements, is fundamental to understanding how ice giants form. And we don't know it. We've never measured it directly. The launch window, if funding is approved, would open in the early 2030s. If launched then, the spacecraft would arrive at Uranus in the early 2040s. That's a long time, but consider what we'll learn. We'll finally know how thick the atmosphere is, how deep the cloud layers go, what the composition of the interior actually is, whether the magnetic field really is generated in the icy fluid layers, whether the moons have oceans, whether Ariel has cryovolcanism, and perhaps most importantly, we'll finally be able to compare an ice giant in detail to what we know about gas giants. Understanding the difference between Jupiter and Uranus is not just academic. Most exoplanets discovered so far fall into the size range between Earth and Neptune. Understanding how ice giants form and evolve is directly relevant to understanding the most common type of planet in the galaxy. Uranus isn't just a neglected corner of our solar system. It's a key to understanding the universe beyond it. We spent 40 years ignoring it. The next generation of scientists won't have to. Subscribe, hit the bell, and tell me in the comments, which of Uranus's moons do you think is most likely to have life? I'm going with Ariel, but I have been wrong before, until the next mission. Neptune was found by an equation, not by a telescope, not by chance, not by a patient astronomer scanning the night sky, by math. In the 1840s, astronomers noticed that Uranus wasn't moving quite the way it should. Its orbit had tiny deviations, small, persistent irregularities that didn't fit the models. Something was pulling on it, something further out. 2 mathematicians, one French, one English, working completely independently, sat down with Newton's laws of gravity and calculated where that something had to be. They predicted the mass of the object, its orbit, its position in the sky on a specific date. They were right. On September 23, 1846, astronomer Johann Galle pointed his telescope at the coordinates Leverrier had given him. And there was Neptune, within 1 degree of where the math said it would be. It was the first time in history a planet had been discovered by pure calculation before it was ever seen. And what we found when we finally looked closely, just once for a few hours in 1989, was a world so violent, so strange, so full of contradictions that it remains one of the least understood objects in our solar system. By the end of this video, I'll tell you about something Voyager 2 detected at Neptune that 35 years of analysis has still not fully explained. Let's go. Neptune is the furthest planet in our solar system, 4.5 billion kilometers from the Sun. so far that sunlight, traveling at 300,000 kilometers per second, takes 4 hours and 10 minutes to reach it. By the time you see Neptune through a telescope, you are seeing it as it was 4 hours ago. From Neptune, the sun looks like a very bright star, nothing more. It provides roughly 900 times less light and warmth than it does on Earth. And yet Neptune is not a quiet, frozen, passive world sitting at the edge of the solar system. It is the most dynamically active planet in the outer solar system. It has the fastest winds of any planet, anywhere. It generates 2.6 times more heat than it receives from the sun. It has a storm that appeared, vanished, and reappeared in a different location with no warning and no explanation. And its largest moon orbits in the wrong direction, on a path that is slowly decaying, heading toward a catastrophic collision with the planet in approximately 3.6 billion years. Only one spacecraft has ever visited Neptune: Voyager 2. August the 25th, 1989. A flyby lasting a matter of hours. Everything we know about Neptune, every storm, every moon measurement, every atmospheric data point, comes from that single encounter, combined with Earth-based telescope observations and, more recently, the James Webb Space Telescope. One visit, 35 years of analysis, and we are still finding things in the data we can't explain. This is Neptune, the planet at the edge, the planet that was found before it was seen, and the planet that has been surprising us ever since. The story of Neptune's discovery is one of the greatest intellectual achievements in the history of science, and it begins with a wobble. By the 1840s, astronomers had been tracking Uranus for decades since its discovery in 1781, and something was wrong. Uranus's observed position kept diverging from its predicted position. Not by much, tiny deviations, fractions of a degree, but persistent, systematic, pointing in specific directions at specific times. Either Newton's laws of gravity were wrong, or something was pulling on Uranus from outside. Two men decided independently to find out what. Urbain Le Verrier in Paris, John Couch Adams in Cambridge, both working alone, both applying the same mathematics, using the observed perturbations of Uranus's orbit to reverse engineer the position, mass, and orbital elements of whatever was causing them. This was not a simple calculation. It required solving what is essentially an inverse gravitational problem. Given the effects, find the cause. The mathematics involved were at the frontier of what was computationally possible in the 1840s. Le Verrier worked on it for years. In September 1846, Le Verrier sent his predicted coordinates to astronomer Johann Galle at the Berlin Observatory. His letter arrived on September 23rd. That same night, Galle pointed his telescope at the predicted position. Neptune was there, within 1 degree of Le Verrier's prediction. It was the first planet in history found not by observation, but by the predictive power of mathematics. It was a direct experimental confirmation that Newton's gravitational theory worked across distances and timescales no one had ever tested it on. Adams had reached similar conclusions months earlier, but the British astronomers hadn't acted on his prediction in time. The French got credit for the discovery. The British contested it. A diplomatic incident nearly erupted between France and England over a planet. But beyond the politics, what this meant for science was profound. The universe was, at its deepest level, mathematical. The positions of objects billions of kilometers away could be calculated from first principles. Prediction and observation matched. Neptune's discovery didn't just add a planet to the solar system. It proved that mathematics is the language of the cosmos. And then Voyager 2 arrived and showed us that even the math only gets you so far. Because what was waiting at Neptune, nobody had calculated. Neptune is an ice giant, like Uranus, but with one critical difference: it is alive. Where Uranus appears featureless and calm, Neptune is visibly dynamic. Active cloud systems, dark storm ovals, bright cloud streaks racing around the planet at enormous speed. A planet that looks from the outside like it's doing something. And yet Neptune is colder and further from the sun than Uranus. It receives less energy. By every passive measure, it should be quieter. The reason it isn't comes down to that internal heat. Neptune radiates 2.6 times more energy than it receives from the sun. Its interior is hot, actively hot. Whatever process is generating that heat, gravitational compression of its interior, slow cooling from formation, radioactive decay, it's pumping energy into the atmosphere continuously. That energy drives the winds, feeds the storms, creates the dynamic, visually striking atmosphere that made Voyager 2's images so dramatic when they arrived on Earth in 1989. Uranus, as we covered, has almost no internal heat. Neptune has enormous internal heat, same composition, same size, same distance category, completely different energy output. We don't know why. Neptune's bulk composition mirrors Uranus, a thick hydrogen-helium atmosphere over a vast interior of hot pressurized water, ammonia, and methane ices, a supercritical fluid ocean. Below that, a rocky silicate core. The methane in Neptune's atmosphere, as with Uranus, absorbs red light and reflects blue. But Neptune's blue is noticeably deeper, more saturated, more vivid than Uranus. An additional blue-enhancing compound in its atmosphere, possibly a hydrocarbon haze at high altitude, makes Neptune appear the richest, deepest blue of any planet in the solar system. A color so intense it looks almost unreal, like someone turned up the saturation. And at depth, as with Jupiter and Uranus, diamonds form and rain downward through the interior. Neptune almost certainly has a layer of diamond precipitation accumulating around its core. Millions of tons per year. An ocean of liquid diamond, possibly at extreme depths. 3 planets in the outer solar system raining diamonds. That is not a coincidence. That is physics. The fastest wind speed ever measured on any planet in our solar system. 2,100 kilometers per hour. That's on Neptune, not Jupiter, not Saturn, not on a planet right next to the sun. On the planet furthest from the sun, receiving the least solar energy, in the coldest region of the solar system. The fastest winds in the solar system are in the place that should have the least energy to drive them. This is the Neptune paradox, and it connects directly to that internal heat. On Earth, winds are driven almost entirely by solar energy. Temperature differences created by uneven solar heating drive pressure gradients. Pressure gradients drive winds. Jupiter and Saturn have powerful winds, driven partly by solar energy, partly by their enormous internal heat. Neptune's internal heat is so large relative to the solar energy it receives that the internal heat completely dominates. The atmosphere is driven from below, not from above. The contrast between what the deep interior is doing and what the cold upper atmosphere is doing creates enormous temperature gradients, enormous pressure gradients, and the result is wind speeds that dwarf everything else in the solar system. The winds at Neptune's equator move west, opposite to the planet's rotation. The planet rotates east, the wind goes west, at 2,100 kilometers per hour. If you were standing on a platform in Neptune's cloud tops, which you cannot because there is no surface, the wind would be moving past you at roughly 600 meters per second. The speed of sound is 340 meters per second. You would be standing in a wind moving at nearly 2 times the speed of sound, continuously, with no break, no calm zone, just relentless supersonic wind. And within those winds, storms form, dark storms, circular anticyclones, the most dramatic of which Voyager 2 photographed in 1989 and named the Great Dark Spot, a storm the size of Earth, swirling in Neptune's southern hemisphere. It was gone by 1994 when the Hubble Space Telescope looked for it, vanished, without a trace, in 5 years. And in 2016, Hubble found a new Great Dark Spot in the northern hemisphere. New location, new storm, same type. Neptune doesn't maintain its storms like Jupiter does. It creates them, runs them, and dissolves them. The atmosphere is too dynamic, too energetic to let a single storm persist for centuries. The Great Red Spot of Jupiter has lasted 350 years. Neptune's storms last years. Then they're gone. And nobody fully understands why they form or why they disappear. Every large moon in the solar system, every single one, orbits its planet in the same direction the planet rotates. Every one, except Triton. Triton orbits Neptune in the opposite direction, retrograde, going against Neptune's spin. This is not a small irregularity. This is a fundamental violation of how moons form. Moons form from the same disk of material that formed their planet. They form rotating in the same direction. That's how the physics works. That's how every other moon in the solar system formed. Triton did not form around Neptune. Triton was somewhere else, moving in a different orbit, caught by Neptune's gravity at some point in the solar system's history, and captured into orbit. Where did it come from? Almost certainly the Kuiper Belt, the vast region of icy bodies beyond Neptune's orbit. Triton's composition, its density, its surface properties, all match Kuiper Belt objects like Pluto and Eris almost exactly. Triton is, in all likelihood, a Pluto-sized Kuiper Belt object that wandered too close to Neptune and was gravitationally captured. It is the largest captured moon in the solar system, and one of the most geologically active. Voyager 2's flyby revealed a surface of extraordinary complexity. Nitrogen ice plains, pink-tinted frozen nitrogen and methane, strange cantaloupe terrain that looks like nothing else in the solar system, and geysers. Active nitrogen geysers erupting from the surface, shooting dark plumes several kilometers high into the thin atmosphere. On a captured Kuiper Belt object, at -235 degrees Celsius, in the outer reaches of the solar system, active geysers. The energy source is not internal heat. Triton is too cold and too small for significant radiogenic or tidal heating. The geysers are solar-powered. As feeble as Neptune's sunlight is, it's enough to penetrate the transparent nitrogen ice surface, warm a thin layer below, and cause nitrogen gas to erupt upward. A solar-powered geyser at the edge of the solar system. But here's the dark side of Triton's story. Because it orbits in the wrong direction, tidal interactions with Neptune are slowly draining Triton's orbital energy, very slowly, millimeters per year. But in approximately 3.6 billion years, Triton will cross the Roche limit, the point at which Neptune's tidal forces overcome Triton's own gravity. It will be torn apart. Triton will be destroyed by Neptune, and its material will form a new ring system, possibly more spectacular than Saturn's rings are today. The most dramatic event in the future of our solar system. slow, inevitable, already underway, and we have a front row seat in 3.6 billion years. Voyager 2 flew past Neptune on August 25, 1989. In those few hours of closest approach, it collected more data about Neptune than all previous observations combined. Images, magnetic field measurements, atmospheric composition readings, temperature gradients, moon surveys, and it found something in Neptune's magnetic field that 35 years of analysis has not fully explained. Neptune's magnetic field, like Uranus's, is dramatically offset from its rotation axis, tilted by 47 degrees, offset from the planet's center by 0.55 planetary radii, more than halfway to the surface. This matches Uranus. Both ice giants have wildly anomalous magnetic fields. The leading explanation, that the field is generated in the electrically conducting icy fluid layer rather than in a metallic core, is reasonable and probably correct. But here is what doesn't fit. Voyager 2 detected distinct, localized regions in Neptune's magnetic field where the field lines converged in unusual ways. Not the smooth, dipole-dominated pattern you'd expect even from a tilted off-center field. Patches, irregularities, concentrated field regions that moved as the planet rotated, sometimes aligned, sometimes not. Some researchers have proposed these features indicate a more complex multipolar magnetic field. Not just a tilted dipole, but a field with multiple centers of generation. A chaotic field that's being generated by convective cells in multiple locations in the icy fluid interior simultaneously. If that's correct, and the evidence points in that direction, then Neptune's magnetic field is not just tilted and off-center. It is fundamentally different in structure from any other planetary magnetic field we know. Not a dipole with complications, a completely different kind of field. And the implications go beyond Neptune, because most exoplanets we've detected are Neptune-sized or slightly smaller. The Neptune mass planet category is one of the most common planet types in the galaxy. If Neptune's magnetic field is representative of how ice giants work, and there's reason to think it might be, then most of the magnetic fields we've been assuming for billions of exoplanets are simply wrong. Neptune is not a remote curiosity at the edge of the solar system. It is a template for the most common kind of planet in the universe. And we still don't understand it. We have visited every planet in the solar system: Mercury, Mariner 10, and Messenger, Venus, dozens of Soviet and American spacecraft, Mars, rovers, landers, orbiters, a helicopter, Jupiter, Pioneer, Voyager, Galileo, Juno, Saturn, Pioneer, Voyager, Cassini, 13 years in orbit, Uranus, Voyager 2, 6 hours, Neptune, Voyager 2, a few hours, 8 planets, and the last 2 have had exactly 1 visit each, flyby only, decades ago. The case for a Neptune mission is overwhelming, and has been for years. But Neptune is far. A mission there takes roughly 12 years of travel time, depending on the trajectory. The window for a gravity assist from Jupiter, which dramatically shortens the travel time, opens in the early 2030s and won't return for another 12 years after that. If a mission doesn't launch in the early 2030s, the next viable window is the mid-2040s. The good news, mission concepts exist. The Neptune Odyssey mission, studied by NASA and Johns Hopkins APL, would be an orbiter and atmospheric probe, spending years in the Neptune system. It would orbit Neptune, conduct multiple Triton flybys, and send a probe into the atmosphere. What would it find? The composition of the interior, finally measured directly, not inferred. The magnetic field mapped in 3 dimensions over multiple orbits instead of a single flyby. Triton's geyser fields photographed at resolutions thousands of times better than Voyager 2's images. Evidence for or against a subsurface ocean on Triton. And potentially, data that helps us understand the magnetic fields and interiors of the billions of Neptune-mass exoplanets we've detected around other stars. Neptune is not just the last planet in our solar system. It is the most relevant analog for the most common type of planet in the galaxy. Studying Neptune is studying the universe. We have now covered all 8 planets in the Space Explorer series. Mercury's impossible iron core, Venus's runaway greenhouse, Mars's lost oceans, Jupiter's role as protector and architect, Saturn's dying rings, Uranus's 40 years of neglect, and Neptune, found by equation, driven by mysterious internal heat, guarded by a doomed backwards moon, its magnetic field unlike anything else we know. 8 worlds, each one stranger than we expected, each one full of questions we haven't finished answering. And we are, right now, living in the era when we begin to answer them. Subscribe, hit the bell, and tell me in the comments, which planet in this series surprised you the most? I already know my answer, but I want to hear yours. Until the next mission.